we're going to move on to Hamiltonian mechanics. So if you are comparing Lagrangian mechanics and Newtonian mechanics and Hamiltonian mechanics, a lot of the advantages that exist for Hamiltonian mechanics also exist for Lagrangian mechanics and vice versa when you're comparing them to Newtonian mechanics, especially in the examples that we're going to be talking about today, because we're not really going to see some of the more elaborate advantages. Now, what we'll see is that Hamiltonian mechanics are a little bit more flexible with the coordinates that you use than Lagrangian mechanics. And for most systems, the Hamiltonian corresponds to the total energy. In particular, this happens when you are working with a system that does not have any dissipative forces, and therefore, as well, where the Hamiltonian does not have any explicit time dependence. So this is nice because it gives us a clear physical significance to the Hamiltonian, whereas for the Lagrangian, there wasn't a clear physical significance. And at least the way that we're going to approach it here, it's mostly going to be an alternative to the Lagrangian, so we won't necessarily see all of the benefits that would come up with quantum mechanics. And we are going to derive Hamilton's equations of motion using the Lagrangian equations of motion. So it's not totally independent of the Lagrangian formalism. It's enough to convince you that this is in fact valid. So let's start with the basic variables. And so we're going to redefine or refresh our memory on Lagrangians. The Lagrangian is the kinetic energy minus the potential energy. And then Lagrange's equations say that partial L, partial Q sub I for each of the I different generalized coordinates is equal to the time derivative of partial L, partial Qi dot. So we'll find in a Lagrangian approach, we're going to find our Lagrangian, write it in terms of our generalized coordinates, which do not have to be x, y, and z. They can be things like theta or phi. And then we apply Lagrange's equations, and we can get a bunch of different equations, which are typically second order differential equations that we would have to solve. We also defined the generalized momentum, and we are going to use this as well when we talk about Hamiltonian mechanics. And this is the partial derivative of the Lagrangian with respect to the Qi dot. So this is d dt of pi. We are going to define our Hamiltonian, and I'm going to use a script h, which only looks a little bit different from, my script h only looks a little different from regular h, but I try to draw it slightly different. Pi Qi dot minus the Lagrangian. And we are going to explicitly write the Hamiltonian as a function of the Qi dot and the Pi instead of as a function of the Qi dot, the Qi and the Qi dot. Now, in some sense, these are a little bit redundant because the Pi are really functions of the Qi, but by explicitly defining the Hamiltonian in terms of Qi and Pi, and the Lagrangian in terms of Qi and Pi and Qi dot, we will have ever so slightly different. There's a different philosophical approach behind it. All right, so with the Lagrangian method, if you have n different Qi, then you have n different second order differential equations that you're trying to solve. With the Hamiltonian approach, you're going to have, if you have n different Qi, you're going to have 2n different first order differential equations that you will solve. And we also call this the momentum conjugate to the Qi. And we will define the combination of the Q's and the P's as our phase space. And this is slightly different from the state space. So this is phase space. in chapter 12, we use the Q's and the Q dots and describe this as state space. And so here there's not explicitly derivatives involved. So the phase space has some geometric properties which make it a little more convenient than state space. And the Hamiltonian is best suited to cases where we do not have dissipative forces, so energy is conserved. We assume the forces if we assume the forces are conservative, that works. So then we're going to work on deriving Hamilton's equations, and I am going to write examples in a different color. So here we're going to start with our Lagrangian, and our Lagrangian is going to be T, which is going to be a function of the Qi and the Qi dot. And our potential is going to only depend on the Qi, only on the position, not on the velocities. And we do that because if we have some type of conservative force, it will not be dependent on the velocity. Keep in mind, as an example, a plane pendulum, where what's meant by that is that the motion is constricted to a plane. So you can only get motion back and forth in one direction. And if we do that, if we consider that as our example, then we can write the Lagrangian for a simple pendulum as 1/2 mL squared, where that is the length of the pendulum, not the angular momentum, phi dot squared, minus mg L 1 minus cosine phi. And here, this is here's my pendulum. This is an angle theta from the normal. And this length is L, this is phi, not theta. This angle is L cosine theta, and this distance is L, so the height above your 0 point is L times 1 minus cosine theta. We can also consider the example of a bead on a wire, which we visited a couple chapters earlier. In that case, you have 1/2 m x dot squared plus y dot squared. And so here your wire can be any arbitrary shape. So we will say that the shape is some function of x. And then minus mg f of x. And what we showed to get this as a function of one variable is that dy dt is equal to dy dx dx dt. So this is equal to the derivative of f with respect to x times x dot. So that means that for this particular case, our Lagrangian is 1/2 m 1 plus f prime of x quantity squared x dot squared minus mg f of x. So we can generally write, in this case, where we have only non-dissipative forces, that our Lagrangian is, in fact, (1/2) times some function, which in general can be a function of Q times q dot squared minus the potential as a function of q. So if we, as soon as we say that the system has to not have no dissipative forces, we have only a dependence here on the position, and then there may be some manipulations here in order to write this as a function of the qi, but we in fact can always find something like that, and we will see that there is then a quadratic dependence on qi dot, or on the q dot. And with that setup, we can look at the derivation of Hamilton's equations. And we're going to start in one dimension because one dimension is enough. We will write them down for more than one dimension. But Taylor leaves the derivation in multiple dimensions as an exercise in the homework problems, which means that it involves a lot of dumb, ugly algebra. All right, so we will start with assuming that we have a Lagrangian of this form with only a quadratic dependence on q dot, and this will give you, for the Lagrangian, a second order differential equation in q. In one dimension, our Hamiltonian is then p q dot minus L. If we write our Lagrangian like this, we will have some simplifications. So we can take this definition here, and we will see that P is A of Q times Q dot. And then this term here, P Q dot, is equal to A of Q, Q dot, times Q dot, which happens to be equal to 2t. So in that case, this is 2t minus the Lagrangian, which is t minus u, or this works out to be t plus u, the kinetic energy plus the potential energy. And we can always define our qi in this case because we will always have P equals A of Q, Q dot. So we will have Q dot equals P over A of Q. So we can always solve to get Q dot as a function of the momenta and this function A, whatever the function in the kinetic energy with these generalized coordinates. So whenever Q dot appears in the Hamiltonian, we can replace it by Q dot as a function of Q and P. So then we will explicitly get our Hamiltonian as a function of Q and P and not as a function of Q and Qi dot. All right, so we want to derive Hamilton's equations, and because our Lagrange's equations involve derivatives of the Lagrangian, let's start by taking the partial derivative of the Hamiltonian. In that case, we will use this form. So in one dimension, this is PQ minus L. So if I simply apply a partial derivative, here I use my product rule, and then I have the partial derivative of the Lagrangian. So here I have P times partial H, P times partial Q, this should be dot. P times partial Q dot partial Q yes, and here P does not have any dependence on Q, so when we take our partial derivative, we don't need that term, but our Lagrangian has dependence on Q, so we have partial L, partial Q, plus partial L, partial Q dot, partial Q dot, partial Q. And then here, we don't have to worry about the P's because we have chosen to express our Hamiltonian as a function of P and Q, but we do not want the Q dot dependence in our partial derivative of our Hamiltonian because Q dot is not, H is not a function of Q dot. We have chosen to stick with Q and P. All right, so then we can use our definition of the generalized momentum, and this turns out to be P. So we have a P, partial Q dot, partial Q, minus P, partial Q dot, partial Q, and those two terms cancel out. So we get the first of our, the first equation. We get that partial H partial Q equals negative partial L partial Q, except now we can use Lagrange's equations, and this is negative d dt partial L partial Q dot, and then this is in fact d dt of P, so this is P, negative P dot. And our first equation is then partial H partial Q equals negative P dot. We can look for our second Hamiltonian equation of motion by taking the partial derivative now with respect to P. Now here we have the P dependence here that gives us a Q dot, and then there can be some P dependence in this term, so we have a plus P partial Q dot partial P, and again that's because Q dot is not our valid coordinate. It's not one of the, we've chosen to stick with P and Q. And then here, minus partial L partial Q dot, because there's no explicit dependence of the Lagrangian on the P. Partial, so we don't have to worry about the P term, partial Q dot, partial Q. And again, this guy is the momentum, is the generalized momentum, so these two terms cancel out. And we are left with partial H partial P is equal to Q dot. So I'm going to write that one here as well. Partial H partial Q is equal to Q dot. And that is our second Hamilton equation. So here we have our two Hamilton's equations for motion. All right, so then we can use this for an example, and this is example 13.1. We have a bead on a straight wire. Not the most interesting example, but nevertheless, we can easily write down the Lagrangian, which is T minus U, or 1/2 mx dot squared minus the potential, which in general can be a function of x. We can apply our Lagrangian equations. Partial L partial x is equal to negative du dx, and this is equal to the time derivative of partial L partial x dot, which this first derivative, the partial derivative of L with respect to x dot, is mx dot. Apply the second derivative, and we get a second dot. So this tells us that the force, this is equivalent to the force being equal to the negative derivative of the potential with respect to x. And then we can define our generalized momentum as partial L partial x dot. So that is mx dot, which in this case happens to simply be the linear momentum. We can then try the Hamiltonian approach. H equals px dot minus the Lagrangian, but we now want to explicitly write it in terms of the momentum and not the position. So here, p dot x, so here I can write x dot equals p over m. So this turns out to be p squared over m minus 1/2 p squared over m plus u, or 1/2 p squared over m plus u, which is our familiar total energy. Hamilton's equations say partial x, h partial x is then equal to negative, well, sorry, partial h partial x is du dx, which is equal to negative p dot. And that is one of our equations. Our second one, partial h partial q, sorry, in this case q is, I have, this one should be a p. I have a typo. Yes, this should be a p. Partial h partial p is then p over m, and that is equal to x dot. We can also look at the Atwood machine. So here we're going to put our pulley here. We have two masses. Our masses will be called M1, M2. This distance we will call X. This distance we will call Y. Although the system is entirely determined by one coordinate, Y. Then, because these are connected, y dot equals y. If I wanted to write my equation of constraint, I would have some r here, and then the length of the string is equal to x plus y plus pi times r. That also tells me that x dot equals negative y dot. And when I put together my kinetic energy, T equals 1/2 m1 plus m2 x dot squared, because when I square it, the negative sign here goes away. And U, the potential energy, we are going to define the potential to be 0 when the two masses are at the same height. Our potential we'll write as negative m1 minus m2 gx. So if the two masses are sorry, that's not if the masses are at the same height. If the two masses are equal, then the potential energy is 0. Here you can define it as anything up to an offset. And what will happen is that, so if you defined the potential energy, let me just do something and show that the choice is arbitrary. So we'll set our 0 here, and then the potential is negative m1 gx minus m2gy, but we're going to use our equation of constraint in order to get rid of y. So this is negative m1g x minus m2g L minus x minus pi r. So this is negative m1 minus m2 gx, where I've collected the x terms, minus m2g L minus pi r. This is an arbitrary constant. Really, you can throw it in there if you find it easier to derive a potential energy like that. I personally often do, because it's a little easier to use an unambiguous definition, as opposed to this requires, I'd have to think a little bit about what the zero is correctly there. All right, so this gives us our the components of our Hamiltonian, and then we want to use this to be able to get all of our equations. So we're going to start here. If the Lagrangian has no explicit dependence, if the potential has no dependence on the QI, this guy happens to work out to be partial T partial Q dot. And that is often an easier form to use. So we're going to go ahead and use that here. And our momentum in that case is partial T partial X dot. That is going to give us m1 plus m2 x dot for P. And then we can rewrite the Hamiltonian as P squared. So I have x dot equals P over m1 plus m2. So here I have P squared over 2m1 plus m2. And then minus m1 minus m2 gx. All right, apply Hamilton's equations. We will start here. X dot equals partial h partial p, and that is going to give us p over 2, or sorry, is p, the 2 goes away when we take the derivative, p over m1 plus m2, and then we can apply this one, partial h partial x equals negative m1 minus m2 g, and that is equal to negative p. So I get from this equation that p is m1 minus m2 times g. And, sorry, that should be p dot. I'm terrible about dropping these dots. All right, then I can take the derivative of this, and I get x double dot equals p dot over m1 plus m2, and I have p dot, so x double dot equals m1 minus m2 over m1 plus m2 times g. All right, so this is the same thing that we would have gotten using Newton's equations, except now we've done it using partial derivatives instead of free body diagrams. All right, we can then move on to Hamilton's equations in several dimensions. I've actually already used this notation, but we're going to define the collection of all of our generalized coordinates. Q as a vector, Q1, Q2, Q3, onto the Qn. And we will define a similar vector for our generalized momenta. And we will then make several assumptions that basically boil down to Lagrangian mechanics is valid and everything behaves nicely and neatly with no messy forces that we don't know how to work with analytically. So we will start with assume that all of the constraints are holonomic, or that means the number of degrees of freedom is equal to the Qn. But remember, when we talked about holonomic constraints, one of these examples was that, for instance, of a non-holonomic constraint is that you have a ball rolling around on the floor, and because depending on the way the ball rolls, you might end up with a different point on the top of the ball. That is a non-holonomic constraint because it's going to give you different final states depending on how the system moves. You can also have other examples like a ball bouncing up and down on the floor. The constraint is that it cannot go through the floor. We can't write that mathematically as an analytical function that we can take derivatives of. It's an inequality. So that is a non-holonomic constraint. We are going to assume further that all of our non-constraint forces can be derived from a potential energy function. It isn't required to be conservative. It can depend on T, but they have to at least be described by a potential energy function. And we are also going to assume that the mapping from the position vector written as our, for instance, x or x1, x, y, and z, or you could have multiple different components, but we're going to assume that this mapping onto the vector q is not time dependent. So you do not have a changing definition in your coordinates. And if we do that, that basically guarantees that the Lagrangian formalism is valid. So then because we derive the Hamiltonian formalism based on the Lagrangian formalism, we need to have the Lagrangian formalism valid, to be valid. So then, more or less, what we're going to do is write down the generalization of Hamilton's equations of motion to multiple dimensions, because last time we simply talked about one dimension. So our Hamiltonian is the sum over all of the components of pi qi dot minus the Lagrangian, where pi is the derivative of the Lagrangian with respect to the qi dot. And we can, in principle, solve these so that we get the qi dot as a function of the q's, the p's, and time. So no dependent. So this would allow us to eliminate the qi dot from our Hamiltonian equation. And the derivation is left as a homework problem, but the corresponding Hamilton equations are partial h partial pi equals qi dot, and pi dot is equal to negative partial h partial qi. Sorry, not qi, partial q. So again, the Hamilton approach leads to 2 at times n first order differential equations, whereas the Lagrangian approach leads to 1 and second order differential equations. And then we can look at the possible time dependence of the Hamiltonian. So the Hamiltonian can depend on time explicitly, either because the coordinates, the q and p, the phase space itself depends explicitly on time, or, and that can cause the Hamiltonian to change, or because the Hamiltonian can have an explicit time dependence. So, because the Hamiltonian is a function of the q's, the p's, and the t's, well, q's, p's, and t's, q's, p's, and t, because there's only one t. Then, if we want to look at the total time dependence of the Hamiltonian, it is going to be, I've written so many partial derivatives, I just start writing a partial. The total time dependence is going to be the sum of the partial derivatives with respect to each of the components times the, the sum of the partial derivatives of each of the different variables. So what that means is that because we have n coordinates, we're going to have to take our partial derivative with respect to q and then times the time derivative of the q, and then the partial derivative with respect to the p times the time derivative of the p plus the partial derivative of the Hamiltonian with respect to time. So because we have n different components, you're going to get n different terms here. Now we can use Hamilton's equations to try to simplify this. So we will notice that this guy is simply negative pi dot, and this guy here is positive qi dot. So we have negative pi dot qi dot plus qi dot pi dot. So these guys cancel out, and we are left with the time derivative. Always those partials. This chapter has me writing partials constantly. The time derivative of the Hamiltonian is simply equal to the partial derivative of the Hamiltonian with respect to time. So the only time dependence that we can have in the Hamiltonian is any explicit time dependence. If the Hamiltonian does not have explicit time dependence, then the Hamiltonian is constant, and because the Hamiltonian in that case corresponds to the total energy, that implies that the total energy is constant. So in section 7.8, we said that if the QI are independent of time, that the Hamiltonian is equal to the total energy. So for now, we are going to only consider natural components, or those which do not depend on time. And this means that and then if we will further assume there is no explicit time dependence, this means that the Hamiltonian is energy and that it is always conserved. We can then apply this to a three-dimensional problem. This is example 13.3, Hamilton's equations for a particle in a central force field. So one of our old friends that we like to talk about a lot. The book uses an assumption. It says that by conservation of angular momentum, the motion is fixed to the plane. I'm going to cover both cases. So if you have a central force and you have some initial momentum, the force can never apply a torque because R cross P is always equal to 0 because the force is along the moment arm. So what that means is that you can never change your angular momentum. And therefore, you can never move out of the plane once you're in the plane if you have a central force. But you don't have to make that assumption. Because we're going to be talking about plane motion, we're going to use plane polar coordinates. I'm going to add on the term that you would have if you did not make the assumption that you were constrained to a plane, because I think it is a nice exhibit of how you don't always need to see these things at first. As long as you are making valid assumptions, the correct physics will fall out. Okay, so in this case, our kinetic energy is going to be 1/2 m, and then, so here we have r squared equals x squared plus y squared, and we're going to use phi and theta is our, phi and z is our other coordinates. So here, one of our components is our dot squared. That's for the change in r. And then for the change in phi, we have r phi dot quantity squared. And then if we consider possible motion in z, that's just a z dot squared. All right. The mapping between r and theta, or r and phi and z, is constant. To x and y and z is constant. So we have no explicit time dependence, and our Hamiltonian is then the energy. Hamiltonian is T plus U. And then we can get our, we can write our momenta. So I am going to make columns here with r, phi, and z. So our momentum, using this definition, or we also have partial t, partial q, I dot. So this is going to be partial t, partial r dot is just m r dot. P phi is partial t, partial phi dot, which is m r squared phi dot. And pz is partial t, partial z dot, which is mz dot, or just the z component of the momentum. Then we want to rewrite our write our Hamiltonian in terms of the p instead of p and q instead of q and q dot. So here, this is going to give us 1 over 2m pr squared plus p phi squared over r squared. So here, the algebra is a little stupid, but not too bad. You have r squared. You could do it a few different ways. You can solve for theta dot, and you get theta dot is p phi over r squared, and then you plug it in here, and you're left with an r squared. And then here we have, I have to change my colors to stick true to my notation. So here we have pz squared. Okay, So then we have plus u of r, and it is only a function of r because it is a central force. Then when we do apply Hamilton's equations, we can say here r dot is partial h partial pr which is equal to PR over M, and PR dot is equal to negative partial H partial R, which is P phi squared over MR squared, MR cubed minus du dr. Here, phi dot is equal to partial h partial p phi, and that works out to be p phi over mr squared and p phi dot is equal to negative partial h partial phi, and there's no explicit phi dependence, so this is a constant. And so this is telling us that our motion in the r direction, our motion in r looks like a one-dimensional problem, but with a slightly modified force from what is effectively the centrifugal force. And then here, this is telling us that p phi dot, this thing, which happens to be the angular momentum, is a constant. So the angular momentum is constant. We can then look at what happens in our secret coordinate that the book didn't cover, z. So here, z dot equals partial h partial pz, which is pz over m, nothing terribly surprising there, and pz dot is negative partial h partial partial z, and there is no explicit z dependence on the Hamiltonian, so this is 0. So this tells you that the momentum in the z direction is constant. So that means the whole system can be moving at a constant momentum, but you cannot change your momentum in the z direction. All right, so this demonstrates the overall procedure. What we're going to do when we're solving these problems is first choose generalized coordinates qn. Then we're going to write our kinetic energy as a function of qn. We will find the generalized momentum, solve them for the qi dot, which I didn't do explicitly here. Use that to write the Hamiltonian in terms of the p and the p's and q's instead of the q's and q dots. Apply Hamilton's equations. Compared to the Lagrangian approach, this is a few extra steps, but it's not that much extra. And most of the benefits you'd really see if you got into quantum mechanics. All right, we can then apply this to a different situation because it basically works for every type of problem you can come up with. I think this one is a little bit contrived, but hey, it's still an example. So we have Particle which is constrained to move on a cone. And we will describe our cone as rho, which is equal to the square root of x squared plus y squared equals c times z. So it is constrained to move in a cone. That's not the world's best drawing. You can always go to the book for better artwork. And then we can write our kinetic energy as 1/2 m and then rho dot squared plus rho phi dot quantity squared plus z dot squared. And because rho is c times z, that means that rho dot is c times z dot. And we can use that to eliminate the rho dot dependence and get, and the rho dependence. We will use these two equations to eliminate rho from our kinetic energy. And we get 1/2 m. Now here I'm going to get a 1 plus c squared times z dot squared, 1 plus c squared, z dot squared, and then here I get c z phi dot quantity squared. Okay, and then my potential is going to be given by mgz. And then I can define my momenta. Pz is partial t partial z, which is mc squared plus 1. Z dot p phi is partial t partial phi dot, which is mc squared z squared phi dot. And using that, I can rewrite the kinetic energy, but I'm going to just add the potential while I'm at it so I don't have to write too many things. 1 over 2m. So here I have pz squared over c squared plus 1. From solving this, I'm going to get a 2m in the bottom and the next term too, so I can combine them. P phi squared over c squared z squared. And that's from here. This one's a little bit hairier. The 2m is out in front. When I square this term, I am left with a c squared, a z squared on the bottom. And then my potential is simply mgz. And that's my Hamiltonian in terms of the generalized momenta and the z. Now I can apply Hamilton's equations. First the z with z. Z dot equals partial h partial pz. So that is pz over mc squared plus 1. And then pz dot is equal to negative partial h partial z, which is negative mg. Phi dot is equal to partial h partial p phi, which is p phi over m c squared z squared, and p phi dot is negative partial h partial phi, and there is no explicit dependence on phi, so this is 0. So what this tells us is that p phi is a constant. So this thing is moving with a constant angular momentum. And then z dot, the z dot dependence is a little more complicated. The book goes through a little more evaluation of this particular problem, and it turns out that there's a maximum and a minimum, and it oscillates about them. This is largely left to a homework problem in the interest of time. And because this is such a weird, contrived problem, I am just going to move on. All right, so far, the advantages and disadvantages are similar between Lagrangian formalism and Hamiltonian formalism. The Lagrangian, if it is independent, we can then think about ignorable variables, which is basically when it turns out that one of these things is constant. If the Lagrangian is independent of a given qi, that means that the corresponding momentum pi is constant and it is ignorable. If the Hamiltonian is independent of a qi, then that pi is constant and it is ignorable. That's the same in both cases. Now, I personally often, especially when you're starting with this, I think that it's probably better to not worry too much about ignorable coordinates, because it sort of requires being able to see that the coordinate is ignorable. It will fall out of the applications of Hamilton's equations and Lagrange's equations. But Hamilton's notation is a little bit more convenient for ignorable coordinates. So, for instance, if you use Hamilton's notation, if you have one of the qi, it does not explicitly depend on a qi. Let's take the case of 2 dimensions. Then you have a Hamiltonian, which is a function of q1, p1, and p2. And you have, then this would tell you that p2 is a constant, and your Hamiltonian is actually a function of q1, p1, and some constant. And this really moves this changes the problem, which was 2-dimensional, into a 1-dimensional problem, so it's slightly easier. The simplification is not quite as elegant in Lagrangian mechanics because you're looking at the qi dot, so even though it is ignorable, you will end up having non-trivial equations from the Lagrange's equations because qi dot is not actually the thing that is constant. So you don't have fewer equations, you simply have you have an uglier equation for a thing that is constant. Now, we can look at the case, compare in greater detail Hamilton's equations versus Lagrange's equations. In Lagrange's approach, if we have 1 degree of freedom, the end result of this is a differential equation, which we can write as a function of q, q dot, and q double dot, which is equal to 0. And this we could in fact recast if we wanted. We could say S equals q dot, and then write this as f of s dot, s, and q. The q dot is the partial derivative of the Hamiltonian with respect to pi, which is some function of the Q's and the P's. And that means that we would get a bunch of equations which look like this. The Q, our vector Q, is simply a bunch of functions of Q's and P's. And I did want to point out here, you can see that the Lagrangian equations and the Hamiltonian equations are equivalent because here we've just recast our Lagrangian equation as a first order differential equation of S and Q instead of a second order differential equation of just Q. All right, so here for the Hamiltonian approach, we would then have something equivalent. The the P dot are some functions of Q's and P's. We can combine these into a phase space vector, Q, P, which we would just write. We can also define another function, H vector of Z vector, which is just F and Z. All right, and a large part of the mathematical literature uses this approach where it uses this formalism where your total phase space is given by some functions of Q and P. Both the Lagrangian and the Hamiltonian formalisms are equally valid with different Q. So the Hamiltonian transformation allows for a canonical transformation. So whether we're using Hamiltonian or Lagrangian formalism, you can choose to change your coordinates, and the coordinate change will be equally valid, but Hamilton's equations are invariant under the coordinate change, so you end up with the same form either way, whereas with the Lagrangian formalism, if you change your coordinates, the form of the equations changes. That means that the Hamiltonian approach leads to much more flexibility. This ability of canonical transformations to preserve the form of Hamilton's equations while changing the coordinates means that you can derive for much simpler equations for many complicated systems. All right, so then we can pull on some of the tools that we developed in the previous chapter. We can describe the phase space of a system as this vector which contains the Q's and P's. And just like when we were describing chaos, this will describe the system's position in phase space. And Hamilton's equations define the phase space orbit or its trajectory. And the question is, of course, how do you describe it in more than one dimension? Well, we learned about the Poincaré section in chapter 12, but here we're going to focus on one dimension because it's much easier to draw one dimension. So because phase space orbits are described by a function, so z is equal to h of z, some function of z, z dot is equal to some h of z, you have a specific velocity in phase space for a specific position. That means that if you ever got on the same point in phase space, you would stay in the same space in the same orbit. So if you had two particles that ended up on the same space, they would then have the same velocity and they would be going in the same orbit. That means that you cannot have different trajectories in phase space cross each other, because that means they would have to be at the same place at this, they would have to be at the same point in phase space, which would mean they'd then follow the same trajectory. So if you have 2 points, 2 things that are in the same spot in phase space at any given point, they have to then follow each other's trajectory. They have to be the same orbit. So no different orbit can pass through any single point. And then we're going to look at what this looks like in the case of one dimension. We are going to use our old friend, the simple harmonic oscillator. The kinetic energy is easy here, 1/2 mx dot squared. U is 1/2 kx squared, which we will write as 1/2 m omega squared x squared, where omega squared is k over m. Our momentum is partial t partial x dot, which is mx dot. Our Hamiltonian in terms of the momentum and x instead of x dot is then p squared over 2m plus 1/2 m omega squared x squared. X dot is partial h partial p, which is p over m. And p dot is negative partial h partial x, or negative m omega squared x. So we then have x dot and p. The easiest solution is to eliminate p is to take the derivative of this, x double dot equals p dot over m, which is equal to negative omega squared x. And the solution is x equals some constant cosine omega t minus delta. P is m x dot, so negative m omega a sine omega t minus delta. And our z vector is given by x comma p, or a cosine omega t minus delta, comma, negative m omega a sine omega t minus delta. And this will be an ellipse in the clockwise direction. So here, x, p, and I will start out at some given point, and my p is, my p dot is going to be negative x, and so that means that p is going to move down. My x dot is going to be positive p, so it's going to move out that way. So I will have, that's a very poor ellipse, but I will have an ellipse in this plane. And the orbits have to be ellipses through conservation of energy. And we've actually, so you can take this form and here plug these solutions in, and you get that this is 1/2 m omega squared a squared. And you can actually divide through by 1/2 m omega squared a squared. And this becomes, let's see, this will become x squared over a squared. So divide this by this, and all you're left with is the a squared, plus p squared over m omega a, which is just the amplitude of the cosine, or of the sine here, quantity squared, equals 1. So that is an ellipse, and the semi-major and minor axes are A and NWA. Which one's semi-major and which one's semi-minor is going to depend on the exact numbers there. Because if you had these guys less than 1, M and W are less than 1, then this would be the semi-minor axis, and otherwise this one would be the semi-minor axis. All right, so then if you have ellipses, no two ellipses can ever cross each other unless they have exactly the same A. And that is, so there we see that when we look at a real problem, the different phase space trajectories cannot actually, cannot cross. In general, in n dimensions, the two trajectories can be very different. So it's often not quite as simple, of course, as a simple harmonic oscillator, because very little is as simple as a simple harmonic oscillator. All right, so then we can look at a falling body. This is example 13.6. Our kinetic energy is 1/2 m x dot squared. Our potential energy is negative mgx. All right, so then our Hamiltonian is T plus U, which is P squared over 2m minus mgx. And this will, of course, be a constant because we have no explicit time dependence. Our x dot is partial h, partial p, which is p over m. Our p dot is negative partial h, partial x, which is mg. And we can solve this and get x equals x naught plus p naught t over m plus 1/2 gt squared. This should look very familiar, but now instead of having v naught, we've written it as p naught m so that we can have it in the convenient form for our phase space diagram. And then, yeah, this term should also look familiar. Then we can write p as p naught plus mgt. So this is the same as velocity equals v naught times gt, but we've multiplied through by an m. And what this does is that here, so here when we had an ellipse, and if you had a group of systems that moved around in an ellipse, they would trace out ellipses. And here, if we consider what happens to different systems, so we have x and p, and we will consider a trajectory that starts at, this doesn't have to be the origin. The origin doesn't have to be at 0. If you have a naught, this is going to follow a trajectory kind of like that to a. And then you can move over here somewhere on the x-axis to b naught. And because x as a function of time, you're going to get these parabolas. So it's going to be parallel to this trajectory, and it will end up let's see, let me try to draw it well. They'll end up being, if these two were on a line here, they're going to be up on a line here. And you can do the same thing here from this point. And this point, these will have the same shapes. These two will have the same shape. These two will have the same shape. If you start with the same momentum, you're going to end up with the same momentum, but then you will have slightly different x's where your x gets stretched a little bit more. So if you start out with a C, with a square or a rectangle, you're going to end up with a parallelogram. And this is, we often want to think about this because we are often looking at systems, at large samples of multiple different systems, and we want to know how those systems move as a function of time. So you can talk about the statistical behavior, even if you might not know all of the initial conditions. So for instance, when you do statistical mechanics and you're looking at the properties of large numbers of different particles, then you might trace, you can get equations for the phase-space trajectories given different initial starting points, and you can talk about how a set of systems moves together, how the phase space evolves. And that leads into Liouville's theorem. So we often want to look at a collection of identical systems, such as might be useful in statistical mechanics, where you don't know what happens to each individual gas molecule, but you still want to describe what happens to the large set of all gas molecules. You can often treat a collection of this collection of dots on a phase space diagram as a fluid. I think I'm not quite as big of a fan of this metaphor because fluids, to have a fluid, it also requires a lot of other properties. But it can help to think about this and to think about the set of all different systems as moving through phase space like a fluid. And what you're doing on your diagram is that you're looking at some collection of different points and what happens to them as time evolves and what happens to that shape. So the phase space is going to be described by the initial conditions, and we can describe the phase space velocity. So z is equal to the vector q p. So the phase space velocity z dot is equal to q dot p dot, and this is simply partial h partial p negative partial h partial q. So we can describe this with Hamilton's equation. So it turns out that this cloud of different points can change shape and orientation, but it can't actually change volume. So here, when we had the particle in free fall, and we had a starting point that was a box, which shows 4 different points, what happens as it evolves is that these two ended up at the same spot, only separated by their initial distance on the x-axis, and likewise these guys up here, this has the same length as that, and the only thing that changes is that they're tilted slightly differently, but this has the same height as that. So these two, this square or rectangle has the same area as that parallelogram. So the whole surface moves through phase space. And it might change and morph as a function of time, but it's going to keep the same volume. Every point, because, and we're going to derive this is Liouville's theorem, that the volume remains constant. And we'll start by noting, we already said that the different phase space trajectories can't actually cross each other. What that means is that a point which starts inside has to end up inside because you can't cross the barrier. I have a bunch of different lines that would connect all of these points, but if I had trajectories crossing, then if for one of these points to end up outside over here, it would have to cross another phase space trajectory, and that's not allowed. And you can make the same argument for points outside of the surface, that if it starts outside of the surface, it has to remain outside of the surface. So in 3 dimensions, you can think about the space as if it were a volume. And we're going to start with that because it's easier to think about 3 dimensions than some arbitrary number of dimensions. And we can talk about our velocity. We can think about it as a velocity of fluid. And we're going to imagine that we have a fluid which is expanding. All right, so this is the initial surface and that's the final surface. It's going to move through phase space velocity with it has some velocity like this, v. And if we want to describe the change in volume, the change in volume is going to be the integral over the surface of some vector n hat perpendicular to the surface, dotted with the velocity, times a small amount of change in time over the entire area. So that's the change in volume. That if the velocity is this way, you end up with slightly less change in volume. So the whole thing, if all that's going on is that the different phase space points are moving around on the surface, it doesn't change the volume. If your change in velocity phase space velocity is perpendicular to the surface, then you're going to have the largest change in volume. And so you want the component of the velocity which is perpendicular to the surface and integrate over all parts of the surface. That gives you the rate of change of the volume and then looking over a small segment of time. Then we can rewrite this. The change, I'm going to divide through by delta t and take the limit as the change in time goes to 0. The change in volume per unit time is then the integral over the surface of the dot product of the unit vector with describing the surface with the velocity vector integrated over all surfaces. By convention, we define this unit vector to be pointing out of the surface, out from the surface. So then, we derive this in 2 dimensions, but it is valid in n dimensions. We're going to draw on some calculus here. So this is vector calculus. If you are taking this class at the University of Tennessee, Knoxville, you have had that, but you maybe haven't had your vector calculus chops exercised quite so much. It's okay if you have to refresh yourself a little bit. All right, and then we are going to use the divergence theorem. So first of all, what is the divergence? What is the divergence at all? The divergence is del dot v, which is the partial derivative with respect to x of vx plus the partial derivative of vy with respect to y plus the partial derivative of vz with respect to z. And the divergence theorem says that if you have n hat dot some vector and you're integrating over a surface, this is equal to the integral over the volume of del, that operator, dot v dv, where this is, maybe I will go through here and make my volumes capital V's just to make it clearer what's a velocity and what is a volume. Okay, so we can look at example 13.7, and we're actually going to come back to some of this, so I'm going to leave a little bit on the board and just change my colors. So, example 13.7, shearing flow. Let us use a velocity vector of ky in the x hat direction. So you have the x component, there's only an x component, and it only has a y direction. What that means is that when you are here, your velocity is 0. When you're here, as you go further and further in y, it gets larger. The velocity gets larger, but it doesn't change direction. And in that case, del dot v is equal to 0. And this would tell us that dv dt is equal to 0. So there is no time dependence. And then we can take our little equation and now we're moving back to some more general statements. We can take our equation for dv dt and say that this is, in fact, the same thing as the integral over all volume of del dot v dv. That's also the volume. And then I can look on both sides. I have a volume. So if I take a tiny little segment of the volume and I only look at a small segment of the volume, del dot the velocity, I wanted to make it a volume, but it's a velocity, is 1 over v dv dt. So I'm assuming that I have, so this integral is giving me a small chunk of velocity, 1 over the velocity. So I'm dividing through by the total, I'm dividing through by the total volume, and I get that del dot v is the fractional change in the volume. And this actually generalizes to many dimensions. So, as with many things in this book, the ugly part is left as a homework assignment. So, Liouville's theorem, we take our phase space velocity, q, p, and we're going to look in one dimension at that velocity, which in one dimension, our velocity is z dot, which is q dot p dot. And using Hamilton's equations, this is partial H, partial P, negative partial H, partial Q. And then we want to look at del dot V. This is partial Q of Q dot plus partial P of P dot. And then I'm going to use Hamilton's equations to write this as partial Q of the partial derivative of the Hamiltonian with respect to the momentum plus the partial derivative of, with respect to P, of the negative Hamiltonian with respect to Q. And because we are physicists, we are working in with nice, neat function space. We're describing real physical systems. So this is, so these are smooth derivatives, and we can switch the order. And this turns out to be 0. So this says that the fractional change in volume as a function of time is 0. So whatever region you're looking of phase space you're looking in, the volume in phase space does not change as time goes on. And this turns out to also be valid with a time-dependent Hamiltonian. And this is actually one of the advantages of the Hamiltonian over the Lagrangian approach, because when you're talking about these systems of particles, the Liouville's theorem says that the volume in phase space stays the same, and you don't have a corresponding theorem that applies to Lagrangians.